Hello, everyone. It's great to be here at Unreal Fest. To be honest, I'm a little bit intimidated because it's my first Unreal Fest, so I'm very happy to meet you all. Um, so today I'll be introducing a quite a new topic for the community, I think, which will be about spectral rendering. But before that, just a quick word about myself. So I'm Thomas Lobberdance. I have a PhD in material appearance and characterization. So for those who just attended Mike's talk about portal to reality, it's the right continuity into this kind of topics. And then I joined UVR about 3 years ago as a project engineer at first. So I really dived into my customers' problems and why they were aiming at this type of solutions. And evolving into the company, I went more on the sales side. But the idea is that I could talk with you about your problems if you encounter some in your visualization workflows. So before I dive into what spectral rendering actually is and what it aims at doing, I just wanted to show you a quick video to just showcase what we're able to do with our products. All right. Yeah, you can clap because those teams work really hard on this, and we're very proud to announce what we have to announce today. I'm not going to spoil, but we have a special announcement by the end. Um, so, well, this video sums up really nicely all of the things that we're going to go over in this presentation, and if we just go over some shots and renders that we made, you're able to capture all of the industries that we aim at enabling, going from automotive to luxury, as we are able to represent jewels or other luxury items at the highest level of accuracy. But also all of the transport industry, not just automotive. So here you have aeronautics, but it could also apply to trains. And the main target is really to bridge the gap between the world of design and realistic images and the world of engineering. And this is possible by making highly advanced, highly accurate renders and using spectral rendering technology. So, like it said at the end of the video, all of these images were rendered using a new render engine that's called UVR Predict Engine for CAAD. So let's go through the agenda. So first, I'm going to introduce you to what we call CAAD. So you might be familiar with CAD, but what's CAAD? And I'll quickly introduce United Visual researchers in this first part. Afterwards, I want to take you through what is for us the isophotography process. So Mike already talked a bit about it, but I'm gonna add on it, talking about spectral rendering, the why we need it and how we use it. Then I'm going to talk about what we are here for today, which is UVR Predict Engine within Unreal Engine 5. And then we have this special announcement by the end. So what's CAAD? So just to start with a quote, we often hear our customers in the industry saying that industrial digital twin will be true to life or will not be. And in fact, it's really important to understand this critical part of the presentation. It's because if we don't have a visual prototype that looks like it's what we're going to get in the end, taking decisions and making decisions about suppliers, about the product that we put into our vehicle, about the materials that we want to use to do this type of jewels or things like that, we will not be able to use digital technology. We will have to go back to the physical world. And this is where we come in. So CAAD stands for Computer Aided Appearance Design. And this is really what UVR aims at doing. So we're not a very old company. We were founded about 8 years ago. And the goal was it just started with a concept that engineers, they had some great tools to do some engineering work, to get some very high-end values, to get some spectral data about which headlamps they're going to put for the front of their car, what real lamps they're going to have, and what display they will use. But in the end, those values that were really interesting, and at first we could use them as a starting point, but we couldn't really make decisions because we didn't have the overall concept, the context, sorry. If we have the overall context, it means that we need to scenarize everything. We need to have the overall experience that looks realistic and not just physically accurate. And at the other end of the spectrum, if we have a realistic renders but that doesn't fit the physical values, then you're not able to make decision as well. So this is really what we wanted to bridge, where we wanted to bridge the gap. We wanted a tool that would be at the crossroads of optical simulation and isophotographic visualization. And this is why we built we built Predict Engine. It was to provide a physics-based, hyper-realistic render. And all of this based on measurement files that you already have. That's not something that you need to go and look for in the nature, or that you need to work on really hard. You already have those values, but we don't usually use them in these type of workflows, or if we use them, they don't really represent reality. And like I said, the goal was to have a single source of truth, being able to do beautiful shots, realistic shots, some things that we could put a person in and really see the reality, but also take decisions based on values, photometric, radiometric values, and spectral values. And all of this having an uninterrupted digital thread, having all of this in one single tool, one single platform. So our goal was not to create our own platform, as you're going to understand. We wanted to integrate existing workflows such as Unreal Engine. Let me first go through the isophotography process. So we already talked about earlier today, but for those who don't have the notion about this, What's really interesting to do when you are in a design process, in a visualization process, it's to have some reference from the actual world. And the more you have some references, the more accurate your render will be by the end. So of course there's the material part, and we also we'll talk about AXF just afterwards for the material representation. But we have also enabled our customers by using additional measurement devices so that people could have environments. So you're familiar with HDRIs, but the ones that you use are mainly RGB. So if you want to have the correct representation of the lighting, you need to have the spectral input. And this is what this device does over there. It enables you to capture the environment, but each pixel has the spectral data. So that way you have the correct idea of the lighting. Same goes for the lighting that you put inside the scene. So the area lights, even the point lights, if you have some, but you want to assign a spectrum to it or a display, you need to be able to have the actual value. So this is for the setting of the scene, but it's also very important for the cameras. There are some libraries out there. Mike just talked about it for the field of views and for the positioning and for the size of the cameras. But cameras also have one critical aspect when you're interested in color matching. It's the spectral responses of the sensor that is inside the camera, because in fact the sensors, they will not capture the light in the same way, and you need to be able to characterize the sensor if you want to access the highest level of accuracy in a scene. So of course I'm talking about all of those devices, all of those measurement devices. You don't need to do all of this to go towards accuracy. If you have all of this, yes, your simulation will be very good in the end. But being able to place the cursor pretty much everywhere you want, from the design intent to the actual product that you will have in the end, it's what we enable using those platforms like Unreal Engine, and where we take it one step further using the Predict suite. So we take all of those parameters, we put it in our simulation. We combine this with high-end 3D models, with very precise 3D models. It can have a lot of triangles. It can be very heavy because we know that's a problem for the industry. And then you get your optical simulation. So I just wanted to say, just before I dive a bit further, if you have any question at any point of the presentation, please interrupt me. I want this to be interactive. If you have any questions, if you have some doubts about what I'm saying, please interrupt me, and then I'll just repeat the question and just answer. Just to make a small focus about materials. So we talked about, during the event, substrate materials. We talked about AXF materials. All of those materials, they allow to do some very high-end visualizations. But what's really interesting about AXF, AXF is in fact the file format that was introduced by X-Rite. And X-Rite has some very great tools that are available on the market, and they're not that inaccessible. It's quite easy to use, frankly, to scan materials. And what's really interesting is that a lot of the features that are available within this measurement file that is very accessible is defined spectrally. So within the AXF that is already accessible through the Unreal Engine pipeline, and you can already import AXF within Unreal Engine, you do RGB rendering. So you have this real-time, very high-end result. But if you want to take it one step further, you need this spectral data. And this is where we come in. We go and fetch natively those data, and we incorporate them into the rendering to make it even more accurate. And this is true for the angle-dependent color. We mentioned iridescence earlier today, but this angle-dependent color is spectrally defined. Same goes for the coatings, the diffuse, the spectrum, and all of the volume scattering that you might have within a material. So all of those are examples of materials that you have here. You have some snapshots about example of materials, but we support all of the features of AXF, which transforms and gets your pipeline even further. And when we characterize everything, like we do with the devices from before, and when we have those type of materials, this is what we can get. This is the level of comparison that we can achieve with this comparison that we call isophotography. So here, on the right, you have, of course, the photograph, which is very specific because this photograph was taken with a video spectral photometer, which means that for each pixel, you get the luminance value and you get the spectrum. And then we did the same thing in a virtual world. And we had all of those data that we measured from the color checker, from the display, from the glass that is at the floor of the light cabin. We measured the walls. We measured the lighting at the top of the light booth, and then at the end you can achieve this level of comparison. And for each pixel that we selected, we did the comparison pixel per pixel, and we were able to compare the spectrum and not just the RGB color. And studying the spectrum also enables you to see where you might have some actual defects, where you might have some flaws in your measurement process, or where you might have some flaws in your digital process. For example, here on the photograph that you see on the right, you can see that there's a slight rainbow effect from the reflection of the display. This rainbow effect is mainly due to the polarization of the display and how it reflects on the plaque on the ground. And on the simulation, you can see this rainbow effect, but it's less present. It's less accurate. But when we look at, in fact, a pixel coming from the display, you can see that the simulation it has this kind of Reynolds signal. And in fact, it's just because, and we have made sure that it was in fact that, it's because the measurement wasn't as well resolved as the signal that we got from the video spectrophotometer, that we get a slight defect. But that's all right. And my point is to say it's okay to have some defect in simulation because the measurement that you will have will not be perfect. What is a big deal is when you don't know why you get a defect, when you don't know why you get some imperfections in your simulations. And this is a nice transition. So why do we do spectral rendering? A quote that I wanted to add, but I didn't get the chance, was that there is no color, there's only light. And it's true, in fact. If you look at a piece of paper that is white under a white light, then you see it white. But if you look at it under a red light, then you will see the piece of paper red. So in the end, all is about how you illuminate the scene and how you will perceive the scene thanks to the lighting. And here we have a DS4 with a specific color paint. It's illuminated with a D65 spectrum, and here under this illumination, it looks fine. It looks like there's no defect. I mean, the color is a bit weird, but okay, why not? But here, no apparent defect. I will not change any materials in this scene. I will just change the lighting. And here, the door changes. Why is that? Well, here, in fact, what we had from the beginning is two different materials. Here, between this image and this image, we didn't change any material. We didn't change any materials, but the material from the door was different from the beginning. But under a different illumination, a defect will arise. And why is that? It's because it's what we call the metamerism effect. And it's just an example to really make you understand that depending on the illumination and depending on the spectrum that illuminates your scene, you might see some things that you didn't expect in your visualization workflow. And this is just an example to make it really striking, but it's true for every step of the visualization process. If you want to have a correct visualization of a measured car paint or of a leather or any part of the vehicle, having the correct spectral color is essential if you want to be able to trust the color that you see at the end of your process. It is essential. Otherwise, you will have a correct approximation. You might have some fitting sometimes, some things that are great if you are doing some real-time visualization, which is also very important, not neglecting this. But here, if you want to be able to trust the final color that you will have in your process, you need to be able to have the spectral data in your simulation. That's even more true if we're talking about volumetric material. When we're talking about volumetric material, there are a lot of layers, there are a lot of different aspects about the transmission, about the index of refraction that most of the time we define it by, well, an integer. But here, the reality is that for each transmissive component, you have a wavelength dependency. And that's true for the very most basic of glasses. If you take the BK7, BK7 has a spectral dependency on the index of refraction. So if you don't have these spectral components, and this is also true, of course, for the volume scattering, then you might have some beautiful results, but will you have the exact result in the end? Well, we are here to say that you won't. Of course, that's also true for the luxury, because if you don't have the correct index of refraction, doing these, it's just not possible. And trust me or not on this, but this is the raw render from the engine. So this is what's computed in the engine. So how does it work? Basically, the core technology is still a path tracing technology. So most of you are already familiar with the path tracer. But here, carried out with the ray that propagates in the scene, you also have the spectral data and the polarization data that is propagated in this scene. And you have spectral sampling, which means that the light will not be represented as RGB channels, but it will be represented as a continuous spectrum. You will have the polarization effects, which means that you will have the correct refraction, the correct reflection, and the correct scattering within the scene. Of course, you have the material that are spectrally defined, where you can have this complex appearance, and most of all, and that's what I've been saying all through the presentation, you will have a physically reliable output. And I want to challenge people to get this type of render without having a spectral render as a process. All right, we talked a lot about spectral rendering, about Predict Engine, but yeah, you might think, okay, you're here to compete with Unreal Engine. What's the deal? Do you aim at offering something else? Absolutely not. That's not our goal. Our goal was to create a universal API, so we don't have our own proprietary platform. Unreal Engine is in fact the first one where we have integrated the plugin within. So it works just as a connector. So we take all of the data that you already have in Unreal Engine. You make a few tweaks because sometimes you need to add a bit of data to get some spectral representation of the scene. But then once you did these few tweaks, and honestly, it's quite easy to take into account, Then you place all of this within the API, and then you get the render inside the editor, inside inside the editor. This is a typical workflow that you have, and this is why using Predict Engine within Unreal Engine is extremely powerful. From the same CAD data that you import through the datasmith workflow, where you can tessellate and prepare the data and so on, do the normal checks that you already do in your visualization workflow. You take all of the measured data that you have aside from the geometry, the environments, the PBRs, the measured lights, the measured materials like AXF. You put all of this data through Predict Matter, which is another app that we developed through our API, which treats all of this additional data, all of this additional spectral information that you didn't have at first. And then we just add this on top of everything that you already have, the animations, the scenarization that you already have as an input, and we put all of this into Unreal Engine. And then you can use those images afterwards either to have, in fact, an engineering workflow using Predict Lab, where you can do actual optical analysis, go and see, okay, this is how much luminance I have, this is the spectrum I have for this pixel, and have a very advanced analysis. Or you can just go through the classic post process. But what we have experienced is that most designers that try our product, they have a post process that is much more simple than what they had with previous renders, because the basis is so much more accurate than what it used to be. So if the basis is already quite accurate, then the work that you have to do on top of it, it's much more simple, and you have a very few steps to take to get your communication ready images. So it's all well on sound, but in order to show this to you, I had to show you a small preview of what the product looks like within Unreal Engine. So this is, in fact, the product within the tool. So you can do, thanks to the API, some live AXF material edits. All of this is spectral. All of this is interactive, and it's, as you can see, it's not real time per se, but it's really fast. It's what we call a path tracer, so you're familiar with it. But here you carry out the spectral information and the polarization. So here it's what it is. It's a preview. It's not a perfect scene, but it's to give you an idea of all of the things that we can do. And what we can do now, thanks to the API, is to have those live geometry edits. Because before we only had, for other platforms, not even for Unreal, Unreal is really the very first platform where we have the API. But for other platforms, we weren't able to edit as well this scene. This is the first platform where we can have this level of flexibility for the workflow. So like you see, it's live recording of Predict Suite within Unreal Engine. Another aspect that's really interesting is that we worked, in fact, really hard on scalability, because since our whole process is based on GPUs, all of the calculation is based on GPU regarding the rendering, we wanted to be able to scale it on multiple GPUs. And this is what we put in place. So you can either use GPU clusters to distribute the calculation of one single image and have it still being interactive, still see it in your viewport in Unreal Engine, and while being connected to a whole bunch of GPUs. And we can adapt to the architecture that fits to your organization, whether it's on premise or in the cloud. We have tested everything, and we have tested compatibility with several cloud suppliers. So basically, if you want to scale the speed of your rendering, this is completely feasible using this type of process. All right, I've talked a lot about Unreal Engine and Predict Engine, and I just wanted to make a special announcement today. So I said we developed it in Unreal, but in fact today is the official release of the UVR Predict Engine plugin for Unreal. So this is a... Thank you. So we've been working really hard on this. In fact, I mean, the API, we worked about 3 years on it. We worked on the plugin for about a year now. And we're very excited, but it's not in your hands yet. As I wanted to say here today, it's still in a beta version because we need feedback. We need people to use the product. We need to know what are your challenges within an Unreal workflow. But we wanted to make sure that by today we had this Spectral renderer that was ready to go, to have the full support of AXF and MDL materials, RGB and Spectral environment maps, and also complex area lights with IES or Lambertian spectrally defined lights. So, a few things about what's coming. There are some connecting features about the rest of the industry, about the rest of the platforms that are out there. We anticipate in autumn another release within Omniverse so that you get the exact same render within Unreal that you would have within Omniverse apps that are out there. So we wanted to make sure that you had both. We are aware that you need we need to support all of the substrate materials, and it's in the roadmap. So we have support for the AXF, but we need to be able to support the rest of the substrate materials to have this continuous workflow for the industry. And we anticipate to have a stabilized version of Unreal Engine by New Year's. And afterwards, we want to go even further and add to these workflows because it is in the original plugin, but not in this new API version. But we need to work on polarization and measure displays, and we need to go even further on physical cameras. There are already some things within the plugin that you can already try and start using. But we are also very aware that in terms of rendering and in terms of pipelines, most of you are using Unreal, but you're also using Blender. And we also want to enable you to have this continuous workflow for image quality. So this is why we also anticipate a release in Blender in Q1 for 2026. So like I said, we need feedback, we need some user perspective. So this is why we set up a WhatsApp group. So we would be very happy if you could join this WhatsApp group, so that we can post directly on this WhatsApp group all of the latest updates. There are going to be a lot of new releases of bug fixes. And if you can just give us some feedback on this plugin, that would be very awesome to have some consumer base. Or if you're at home, just scan the QR code and you're welcome to join us in our beta user pool. All right. So I talked about for half an hour. All right. So just to sum up, at UVR, we publish Predict Suite, which is a suite of products: Predict Engine, Predict Lab, Predict Matter, even Predict Sky. I didn't mention Sky here today because the goal was to focus on spectral rendering, but it also enables you to have some spectrally accurate skies with polarization inputs. But the goal was to have a tool that is optically true. So we made sure that it's in fact CIE 171 compliant. I don't know if some of you are familiar with it, but it's just to say, okay, this is serious. We also have this integrated plugin completely compatible with Unreal Engine 5.5. It will be with 5.6 and 5.7 when the release is fully out. And yeah, the goal was to have this uninterrupted creation workflow, but it's also interactive and scalable, so that way you can distribute the calculation across your platforms and meet your expectation in terms of rendering. Thank you very much for your attention. I'm not going to keep you any longer, except if you have any questions. Thank you.